So now it's time to talk about what are these z-scores that we talked about earlier, and what does standardization actually mean. So this image is really important here on the right hand side. Standardizing scores is the process where we convert from a raw score to a z-score. So think about it this way. When you're taking your ACT or your SAT, you get so many right out of the total, right? But that's not what they report to you. They tell you, oh, you got a 33, oh, you got a 36, you got a 17, a 12, a 14. And that doesn't mean you got 14 right. It means that that's your standardized score. That is the process that we're embarking on with z-scores. So z-scores, we also call them standard scores, but they're pretty commonly known as a z-score. The reason we like them is it helps us understand where the score is on the normal distribution. So ideally on the normal distribution, our mean is at 0, so that's the middle. And then this is -1, +1, -2, +2. So with those z-scores, I'm really able to say, well, this is where it is in the distribution. And I can calculate that z-score using just the information of the mean and the standard deviation. So if I want to use the formula to actually calculate a z-score, what I would do is take the raw score, so that's how many questions you got right, minus the mean of how many questions everybody else got right, divided by the standard deviation. So that is how we calculate a z-score. It's a bit tricky, and it also involves, I have to find the mean if I don't know it. So it does involve figuring out other scores and what's going on. And the standard normal distribution, my z-score of 0 happens smack in the middle. My z-score of -1 and +1 is 1 standard deviation away. So the further you get from the curve, the less likely you are to score. So if I have a z-score of -2.5, that would be in this darker shaded area, and it's not super likely I'm going to get a score there because most of my scores are happening here in the middle. So that's why z-scores are helpful, is they immediately give me the information that I needed, the range, the variance, and the mean to know earlier. So a z-score can be calculated with either a sample or a population. It just means symbols change. I can use Appendix A in the textbook to understand the percentiles. So I can look up a z-score and get the corresponding probability percent. Whoops. A z-score is going to let me compare performances across data values, but with the same scale of measurement. So if I say a z-score of -1 versus a z-score of +1, I know where it is in that picture, okay? When I start adding other variables in, obviously I have different scales of measurement. And I can also calculate the error in the z-score by knowing how far it is. If I want to find that probability, so that likelihood number I talked about of it being on the darker shaded area, once I have converted my z-scores and I have that normal distribution, here's an example. If I have a distribution where the mean is 100 and the standard deviation is 15, and they say, what is the probability of scoring 130 or higher? So the first thing I have to do is find a z-score. So I'm going to have to do 130 minus the mean, which they just told me is 100, and I'm going to have to take that and divide it by 15. So I'm going to get 30 divided by 15, which is a z-score of 2. Then I'm going to go to table C, and I'm going to look at 2.0, which gives me this probability of 2.3%. So the probability of getting a score between 90 and 100 is going to be taking the probability at 90, taking the probability at 100, and then subtracting those two. So this is definitely easier than getting the between probabilities. If I want to find the raw score, so let's say I'm working in reverse, I want to find the raw score. I can do that if I know several other things. So if I want to know what score marks the 20th percentile of a distribution when the mean is 100 and the standard deviation is 15, I'm going to go into Appendix A, figure out my z value, and then I'm going to reverse engineer the formula for z-score to find the raw value of 87.325. A second example of this would be if I'm supposing the average SAT math score for males is 517, so average mean. The standard deviation is 100, and it forms a natural normal distribution. If I want to find the raw score that goes with the 90th percentile, I'm going to go into my chart in Appendix A and find which one corresponds to a probability of 90th percentile, which is over here, and that's going to be 1.28. Then I'm going to reverse engineer that into my z-score formula to get a raw score of 645. So if I want to convert a raw score into a percentile, I have to go through the z-score. I cannot bypass the z-score process. Once I have the z-score, I'm going to have to go into my appendix, look up the probability, and then that is going to tell me my findings for that value. Here's an example of going from a raw score to a percentile. So let's suppose the person's raw score is a 425 when I know there's a standard deviation of 100 and a mean of 517. How can I convert the raw score into a percentile? Well, I'm going to find the z-score, so right here, and then I'm going to go to Appendix A, and I'm going to go to negative 0.8, and then at the top 0.8, and I get 0.3106. And to get the percentile of that, I'm going to have to subtract it from the middle, and that gives me the 18th or 18.94 percentile. So that process can be a little bit trickier because you're going to have to use your appendix, and then you really have to remember that to find the percentile, you have to subtract the probability from 0.5. And that would be the visual of what we just described. If I want to find the proportion of scores between two numbers, so this time I say, what if I score between a 90 and 100? I have to convert both of the numbers that it's between to a z-score. Then I have to go into Appendix A and find the z-score for the raw scores and find the corresponding probability or proportion for each. If they're on the opposite sides of the mean, meaning one's a positive z-score and one's a negative z-score, I'm going to add them together. If they're on the same side, so they're both negative or they're both positive, I'm going to subtract them. And we have the example over here on the right. If the proportion of my scores is going to fall between 110 and 140 in a population where the mean is 100 and the standard deviation is a 15, I'm going to convert 100 and 140 into z-scores. Now these are both positive, which is important. And so I'm going to find the proportion between them, and I'm going to take that a step further, and they're on the same side, so then I'm going to subtract them, and that is going to yield me to my answer. So in summary, standardizing these scores is really important because I can't make assumptions unless I know the standardization of the curve. It allows researchers to put variables in there that were originally measured using different scales and kind of using one scale. It'd be kind of like when we're working in centimeters and somebody else is working in meters and somebody else is working in inches. There's a whole lot of language conversion that has to happen. If I say 5 units, everyone's thinking something different. The same thing is true in statistics. We need to all be on the same page, which is why we have this one measurement system of the standard normal curve and using z-scores to describe them.